Chuck?
Okay.
Not because we sold you out, but because you want to go.
That's exactly.
I appreciate that.
We sold you out because you wanted to go. Sorry. I buried your teeth.
What?
I want to make him this quick chart quickly. I'll do it.
Absolute Cohen. That's funny.
I just
Okay.
said the other levels would be out.
So here's where we're at with the lab. Okay, this is why this lab takes 3 days. So the first thing that we figured out was the order of the magnitude, okay? So on the order of the magnitude, you should have R equals whatever value K was, okay? And make sure that your K has the correct units. Now, what is rate dependent upon? Concentrations of what?
Oh, acetone and H+.
Your acetone and your hydronium ion, right? Yes.
Yes.
Yes. Should be first order with respect to both of those, unless you're Twig and Twiggy, and then it might be to the 23rd. I'm not sure.
Yeah.
Yeah. You guys broke
That's just a
chemistry.
small margin of error.
Yeah, it's just what
It's an option.
it's a rounding error. Now, so then here, and I think almost all of you got through that next part. Then you said, okay, we're gonna, and this is the whole point of this, is that you're gonna pick a concentration of iodine. And you know that rate equals the change in the concentration of the iodine over time. Then you're gonna go through and you're gonna predict the time. Show me those calculations with the units. Not to throw any judgment on anyone, okay? And then the times that I saw were actually pretty close to the predicted times. Yay for science. Now, here's gonna be the third part of the lab that we're gonna do today. So the third part of the lab is now we're gonna try and find the value for the activation energy. So on your activation energy, if you remember how you gotta do that, you've gotta have a graph. So this is the only graph that you're gonna have to draw. You're gonna plot the natural log of K on the y-axis and 1 over temperature in Kelvin on the x-axis. So this is what you have to run today, is you've got to run this at different temperatures. But this gets a little sketchy as far as the technique goes, especially on the cold side. So what you all have is your rate equals, like 1G, what was the value of your rate constant, your average rate constant?
Okay.
Yeah. bless you.
1.91 times 10 to the negative fifth.
And I'm guessing hopefully that was 1 over molarity seconds, because you've got molarity times molarity, okay?
So.
Now, that's based upon a certain temperature, okay? Hopefully, if you don't have that temperature, just take the temperature of the solutions in there. So that's going to be one of your data points. Now, you're gonna pick one of the 4 trials, okay? I don't care which one, you're gonna pick one of the 4 trials. You already know what the rate is. So let's say you're gonna pick reaction 2. Okay, cool. You already know what the rate is. You have that value. You know what the K value is. You have that value. You're gonna know what the temperature is in Celsius. Let's say that was 20 degrees. Then you're gonna add 273 to it, and you're gonna have 293 Kelvin, okay? So you already have one data set, okay? You already have that number, cool. Now, what we need to do is, now we need to run them at temperatures below that point and temperatures above that point. This is where it gets sketchy in terms of how you're gonna do this. So you're gonna pick one of the reactions, 1, 2, 3, or 4. I don't care, okay? Pick one. It's up to you. But here's what's gonna be important. Let's say that you pick reaction 3, okay? So if you pick reaction 3, you're gonna have in like a beaker or something, you're gonna have the 10 milliliters of your acetone. You're gonna have the 10 milliliters of your I2 in a separate test tube, and then you're gonna have your hydrochloric acid and you're gonna have your water. So you need to mix together the hydrochloric acid, the acetone, and the water in a beaker. okay? Or an Erlenmeyer flask or something, I don't care, pick the glassware, okay? You're gonna mix that. Then you're gonna keep the iodine in a separate one, because you wanna keep the iodine separate because you don't wanna start the reaction until everything is at that temperature. The one you want to do first is gonna be the cold one, because that's gonna take the most time to set up. It's also gonna take the longest time to actually run the reaction, okay? So I've got a chest of ice in there. So what I would suggest is that you take a bigger beaker and you make like an ice bath, okay? And you're going to submerge the container that has the acetone, the water, and the hydrochloric acid in one side, and then you're going to put the iodine in a test tube in the other one. Obviously, the iodine is going to cool down a lot faster because of the fact that you have less volume. Okay, so the iodine is going to cool down really fast. So what you want to do is monitor that temperature until both of those are at about the same point. You don't have to get this down to 0, okay? Get it somewhere around 10 degrees Celsius, okay? I don't want, it's like, oh, let's freeze it. No, this is not the movie Frozen. Just get it, sorry, I like the movie. I'm not bashing.
Have you seen Frozen?
I have seen
Have you
Frozen.
seen Frozen, but you haven't seen Mean Girls?
Exactly.
Have you seen Frozen
is
2?
cultural significance.
No, I've only
I've
seen
seen
Frozen.
those, I haven't seen Mean Girls.
Who said that?
Look at their box office numbers. Frozen performed popular, so it's more important than
I've
Frozen.
seen
I haven't seen
Infinitely more
Cindy, I'll
Frozen
give you a
dolls,
parking
Frozen
lot.
backpacks, Frozen songs
We
on
parked in
radio
different
than
parking
anything about Mean
lots.
Girls.
I'll give you that. Well, that's because they do it better. How do you market Mean Girls? Really? As opposed to like a cute little snowman named Olaf. Come on.
But Mean Girls is such a good movie.
I know that's not the point. What's the marketing? Okay, so this is where you also have to monitor it. So you're going to get everything dropped down to a particular temperature, something around 10 degrees. Just make sure that it's the same. Then you take the iodine and you're going to pour it in there, okay? Now, you can't leave everything in the ice bath because then the temperature is going to continue to drop, okay? But this reaction is going to take a while. So if you set it out at room temperature, it's going to begin to warm up. So you need to monitor the temperature if it gets like warm, okay? And I'm not saying like it's obviously, it would take a long time to get room temperature. But if you start at 10 degrees and it say warms up to like 12, you probably ought to put that back in the ice bath. So this is only going to work if you have like the same temperature. So so get everything cooled down. Start the reaction. Let it go. It's going to take a while, okay? I'll tell you that right now. Depending on how cold, because this is very, very temperature sensitive in terms of the reaction rate. Now, here's the story. So, you're not going to change the values. So you're going to have the same concentrations. But think this through. It's going to take a long time. So since it's going to take such a long time, what's going to happen to your rate? Will it be bigger or smaller than room temperature? Smaller, why?
Less molarity per second.
Yeah, you're dividing by a bigger number, okay? So this is what you need to think through. Oh, okay, at really cold temperatures, you're going to have a smaller rate. But your concentrations are going to be the same as room temperature. So if your concentrations are the same, but the rate is smaller, what's going to happen to the value of your rate constant? It has to become less as well. Okay? So this is why this is lowercase k, because it's temperature dependent. So the k that you have already calculated is based upon a certain temperature, probably around 20 degrees Celsius. K changes depending upon the temperature. That's the whole point of the story. So you're going to calculate over here on page 6, you're going to know what the room temperature values are. There's nothing to calculate. It's whichever reaction that you're going to pick. So tell me which reaction that you're going to pick. 1, 2, 3, or 4. I don't care. Pick one. then you already have everything for the room temperature line. You don't need to run the room temperature line again. You already have that data. What you are going to need is that, and I tell you, the time for the reaction at about 10 degrees Celsius, okay? Tell me, you're going to write down, hey, this is what this temperature is, and then have that temperature in Celsius, have that temperature in Kelvin. Then you're going to recalculate the rate. You're going to recalculate the value of K, lowercase k, and obviously that should be a smaller number. Then you can take the natural log of that value of K and then the 1 over temperature in Kelvin. You have the room temperature. The only thing you need to do with that value is write it down, take the natural log of that, take 1 over the temperature in Kelvin. Now, the one that's at about 40 degrees, now you need to set up the opposite. Now you need to set up a hot water bath. Put that on hot plate, obviously. That's hence the term hot water bath. And shocking as that may be. And then you're going to do the same thing. You're going to take that hot water bath and you're going to have whichever concentration, whichever reaction that you're doing, you're going to do the same one for all three. And then you're going to have your iodine over here. And you're going to run that, you're going to mix that. You're going to monitor that temperature till they're both at about 40 degrees. And again, your iodine temperature is going to change much more rapidly. So you're going to have a hot water bath. Put beaker, Erlenmeyer flask, whatever you're going to use in there. Put your iodine in the other one. Monitor. They both hit about 40 degrees. Mix them together. Now, don't eat, especially on that one, you're not going to have time to like split it up and look at the two different test tubes. Okay, you're not. That's going to happen, bam, like it might take 5-10 seconds to happen. Like it's going to happen fast. So on that 40 degree one, do not let this thing get too warm. Like you don't want to boil this. Like, oh, let's boil it. Let's get it 90. No, okay? Monitor the temperature so that you stop it around 40, okay? Don't let it go to like 80. No, bad things going to happen. Let that warm up to about 40. Get them both at 40, and then mix them together. Have, as soon as you pour that in, have somebody with that stopwatch ready to go. So here's the graph that you're going to have. So you're going to have 3 data points. You're going to have the natural log of K. You're going to have 1 over temperature in Kelvin. I would suggest like you do the little break signs because these numbers are going to be pretty small because you're taking like 1 over 330. So these are going to be pretty small numbers. So don't go 0 and then try and space those out. Okay? Have that. Since you only have 3 data points, listen to me. You're only going to have 3 data points. Take a ruler and you're going to draw a line of best fit. When you find the slope, it has to come off of the 2 points that are on the line of best fit. Okay? You cannot use your data points unless they actually happen to lie on the line of best fit. Okay? This is your lab write-up. It's formal. At some point, I want to see the calculation of that slope. Okay? I want to see, write down the points that you're going to use to find that slope. Show me, oh, change in y over change in x. Okay? With the units. Okay? With the units. Now, what are the units going to be when you take the natural log of K? There is no units. 1 over temperature in Kelvin is going to be 1 over Kelvin. So, this is where the magic happens. So you have no units on the top, and then you're dividing it by 1 over Kelvin. So what are going to be the units for the slope?
Kelvin.
But it's not, this is weird. It's exceptionally rare that this happens. Even though the slope is in kelvins, the slope obviously isn't the temperature because the temperature is changing, but the slope is constant. So the units are Kelvin, but it isn't the temperature. It just happens to be Kelvin. Now, what you're after, okay, and Graham, on the front, there's equation 2, okay? Well, Graham
It's
struggled.
very Regina George of you.
I know, well, Graham struggled with equation numbers yesterday. So, here's the story. So, the slope of this line is gonna equal the negative E sub A over R. And your R is gonna be the ideal gas law constant of 8.314 joules per mole Kelvin. So, to get your activation energy, your slope should be a negative value. So basically, you're just gonna take that slope, which is a negative number, multiply it by that ideal gas law constant, and this is why the units have to work out. Because your slope is going to be in Kelvin, that's joules per mole Kelvin, the Kelvins cancel out, you get joules per mole, that's what activation energy is measured in, okay? Cool with that. So, today is the temperature day. So then, at that point, you can also finish those questions on the back. Let me explain number 10 on that last page. So what I'm telling you, we're going to make an assumption. If the reaction had been first order with respect to acetone, okay, and that's it, there is no other thing. Let's just say it's first order with respect to acetone, and there is no other contributing factor. And I'm going to give you, hey, assume a value of K to being 3.6 times 10 to the negative fifth s to the negative 1. What is the half-life of the reaction? So in other words, if we say, let's say that our data thinks that this is just first order with respect to acetone. Okay, cool. And we know the K value, we should be able to calculate a half-life. So you're going to calculate a half-life. Then when you get to number 11, then I'm going to say, looking at your data, okay, for trial 1, is this a safe assumption? In other words, does that half-life match up kind of with the time that you observed, okay? If it does, hey, maybe we're on to something. If the times are vastly different, we can't make that assumption, okay? So that's the whole point of questions 10 and 11. You're going to calculate a half-life and then go, hey, if this is what's actually happening, does this match the observation? Okay? All right, ready, break. This is due on tomorrow.